Why? Wait, what are you doing? Wait, why? Why'd you do that? Wait. What? I think I just. No, don't practice it.
All right, let's finish K nearest neighbors today, and then we're going to go into decision trees, which is a slight departure from the original schedule, but I don't think you saw that, so it doesn't matter. Okay, so just to remember, KNN was like this, K nearest neighbors is basically the simplest classifier you could possibly come up with. You just look at the neighbors around you according to some distance measure, and then you take their vote. So that's in a slide, the summary of what the method is. And I mentioned that this was a version of a non-parametric model, and that what that means is there's no training phase, and basically the quote-unquote parameters of the model are the training data points and the value k. And so sometimes it's also called instance-based lazy. All right. And then I was showing you the decision boundaries and how they can get more, how they're very complex even with one nearest neighbor, and how they smooth as you increase the number of neighbors. And then we went over this notion of a Bayes error, which is sort of like given that the two distributions of, say, the two classes are only so far pulled apart, then there's some sort of optimal error you could get even with a perfect predictive model. And so one of the nice things that is not in the slide, right? Oh yeah, here it is, I just rewrote it, is that you can show, there's a proof that we didn't go over, that surprisingly this super, super simple model, in the case of one nearest neighbor, has at worst twice this Bayes optimal risk, which is sort of a nice theoretical underpinning for why we might consider using them. And so that's where we left off. And so now I'm going to go through some of the, that's sort of the basics of what is this algorithm, how do we choose K, and things like this. And so now I'm going to talk about what some of the things that can go wrong are. And so one thing that can go really wrong here is when the dimensions are high. And so I'm going to talk a little bit about what's weird in high dimensions, which is true and applicable to K nearest neighbors, but it's also a general phenomenon that you may run into in machine learning. So it's good to understand these things. And if you haven't heard it before, it's actually completely weird and completely counterintuitive. And so I'm going to start off just talking about a circle and asking the simple question of like, do most of the points lie in the ring that's outside the red, so this very thin ring, or do most of the points lie inside? Who thinks they lie mostly inside? Who thinks they lie mostly outside? I guess it's just for me to see who's actually listening. Good, a few people. Right, okay, so that's pretty easy. We can look at it, and sure enough, most of them lie inside. Okay, great. So should that be an exam question? Who wants that on the final? Ooh, that might be the best response rate yet. Okay. Okay, so now what if we go to like a 3D sphere, or more generally to like a d-dimensional sphere, like a hypersphere? Does anyone have an idea of what's going to happen as the dimension goes higher and higher? To me, it's impossible to think of, but I know the answer, so. Does anyone know the answer from reading the notes, or, yeah? Right. Did you say it was in discussion? Oh, it was already in a discussion? Oh, okay, I see. I was getting confused. Right, so, and we can show that. So what's going to happen is, as you go to higher and higher dimensions, all the volume of the hypersphere is going to concentrate on that outer circle, which is completely weird. And so you can show that pretty easily. So there's like a general formula for a d-dimensional sphere, which has this weird factor in the bottom, which is like a generalization of factorial to non-integer numbers, but you don't really need to worry about that. I mean, so this is just like in one dimension, right, in terms of radius, in 2 dimensions, and so forth, and then just know that there is this general formula for d dimension. So now from there, you can do an analysis that says how much of the volume lies in this thin ring. So it's basically the volume of the full thing minus the volume without the inside bit in it. And we can just appeal to the formula from the previous slide to get the volume of that shell. And then we can say what's the ratio of that thin shell, so that's on the numerator, to the ratio of the whole thing. So there's nothing fancy here. I'm just basically saying what's the ratio of the volume that lies in the shell compared to the whole hypersphere. And it turns out to have this formula, but quite simply, like you can just, it emerges exactly from there, nothing fancy. And then you can take the limit as d increases and ask what happens to the volume, the proportion of the volume that lies in a shell of size epsilon. And basically, it goes to 1. So all of the mass concentrates in the sphere. And so this means that a lot of our intuition that we have when we think about machine learning and what's going on in these high-dimensional spaces kind of falls apart. So one of the implications of this is that when you're in very high dimensions, almost all points kind of lie very far away from each other. And so you can imagine that with k-nearest neighbors, this might have some implication. But this is actually just like an empirical curve computing that, and you can see just even like on small, like finite numbers of this is 1,000, that already is basically at 1. And so, and you can also show this for Gaussians, probability density functions, that if you go to higher and higher dimensions, that actually there's basically something called like the typical set that lies in a radius related to the variance away from the center, which I think is also kind of counterintuitive. And so, and as d increases, the density concentrates further and further away from the center. And so, consequently, if you sample from a Gaussian in high dimensions, these will tend to come from this thin shell that is not at the origin of the Gaussian. So, okay, so what does this have to do with k-nearest neighbors and generally machine learning? So you'll often hear of this as the curse of dimensionality. And partly it's a curse maybe because it breaks down our intuition, but it's also a curse because things that we kind of rely on intuitively break down. And so often problems that are relatively easy in low dimensions become really, really hard as the dimension increases because of this phenomenon. And in some sense, like if we could see in these high dimensions, we wouldn't need to do machine learning, right? Like you could just plot things and then almost do things by hand. So we need to be able to operate in pretty high dimensions. And so the implication for k-nearest neighbors is the closest points might be much farther apart than we expect, and like the closest and the nearest points can somehow almost be similar. So kind of very weird things happen, and if you run this in very high dimensions, odds are that it's going to work very badly. And also another way you can think about this is that you're going to have just poor coverage of the space of all possible test points if those points they don't come from that like a region right inside that thin shell. Okay. And so in general, because of this phenomenon, also the amount of data that you require to do well, given that you're measuring distances, is going to increase exponentially with D. And so that's pretty bad. So the question is, how can we mitigate this problem? We know it's going to do really weird stuff in high dimensions, and we can't really trust it. It's probably not going to work. What we really care about somehow is like the ratio of D to N, right? We want lots of data in relatively few dimensions. So we can just try to make N larger by getting more data. And so in some domains you could do that, right? If you're just collecting images and it's easy to get labels or something like this. But of course in many domains you can't just get more data. So the other thing we can do is we can make the dimensionality smaller in a number of ways. So one would be by choosing the most relevant features somehow. And so this is notion of feature selection, which I don't think we have time to go into the course, but if you're interested, I mean, you can just Google this term, and this is a thing people often do in machine learning, is to get the original feature size set down to something smaller using only those that are more relevant. And then the other thing you can do, of course, is you can make D smaller by using some unsupervised technique. So if you have real value, actually even if you don't have real value, you could have used PCA, and there's other things like PCA called factor analysis, things like this. You can reduce the dimensionality, and this also can help you. Okay, so is that any questions? Okay. Great, and then another problem is that when you're doing k-nearest neighbors, so often by default people just use this like Euclidean distance, and in the Euclidean distance, all the features have the same importance because they all get weighted the same in a Euclidean distance. And so, except if they have different ranges. If they have different ranges, then implicitly they're going to end up kind of getting a bigger influence on the Euclidean distance. And so you may not want that. So sometimes what people do in this, and also for other methods, is to normalize the range of each feature. Just take your raw features and maybe make sure they're between 0 and 1 just by dividing by the min, or subtracting min divided by the max, or you can make it 0 mean unit variance. This is sort of a general technique people use if you're worried that the scale of each feature being different will make them have a different influence on the procedure when you don't think that that's appropriate. And then another problem is you might have some irrelevant features, and we mentioned this notion of feature selection, or correlated features that might somehow mess up the distance measure. And that's a repeat. But yeah, you can eliminate some of them, and you can also reweight them. So you could use different heuristics to say, I will just actually downweight some of them. So, and then there's a distance that can be very helpful that's often used with k-nearest neighbors called the Mahalanobis Distance. And it should look familiar to you because it's very related to the first half of the course. And so because it's related to sort of this diagonalization or making a Gaussian, an arbitrary covariance matrix look spherical. And so that's somehow what you're going to do is you're going to kind of decorrelate your features by essentially rotating them, except you're going to make it inside of the distance function. So normally, as I said, a default thing to use in k-nearest neighbors might be just the Euclidean distance squared. And what the Mahalanobis distance does is essentially you would take the inverse covariance matrix and slap it in there just as you would in a similar manner to the kind of diagonalization you saw in the first half of the course. And so what the effect of this is that if you imagine you had two features that were identical, then in the Euclidean distance it's going to get double counted. And once you do this, you basically are sort of essentially decorrelating them, and now they will not be double counted. Right, and so the variables are effectively uncorrelated in this way that's similar to thinking of rotating things using PCA, except you're not truncating the eigenspectrum here, right? You're just rotating according to that matrix. And so, and actually, someone was asking me about this. This is sort of well beyond the scope of this course, but there's a sort of a subfield of machine learning, if you will, called metric learning. So you can also try to learn a distance or a metric that's useful for KNN in a supervised manner with your data. So in this case, this was a pre-processing step, right, that doesn't look at the class labels, it's just looking at the structure of the x's, like the input features themselves. But you can imagine somehow having a parameterized metric that you learn simultaneously in some sort of k-nearest neighbor manner. And so in fact, one of the ways people do it is by maximizing a margin kind of for each point. But we're not going to go into that. Okay, so, right, and then now you might, like, there's this weird phenomenon because this is this instance-based learning or non-parametric, and so to store the model, we have to store all of the data points, and so that incurs order, like linear in dimensions and number of data points, which is kind of absurd. And during test time, the simplest way to find the nearest neighborhood test point is to compute the distance to every other point, and so that's going to be order d times n. And so then you might ask, well, what's the time complexity of the whole algorithm? And so actually it depends which way you do it. And in fact, if you go Google this, you'll sometimes see one answer and sometimes the other. So I wanted to just put them both here. So if you save the distance to each training point from the test point, and now you have this list of distances, and then you want to, and so now you want to then go get all k of the neighbors, then you can loop through each of the distances for each of the k nearest neighbors. And that way you get a time complexity of, first you've computed all the distances like this, and now you don't care on that, you don't depend on the dimensionality for the remaining k, because you just are saving the distance itself. And then the other way would be for each of the k nearest neighbors, just scan the whole data set and pick out the k nearest one. In that case, you actually are using the dimensions each time, so that's just d and k. And so, we need lots of data for this, for k nearest neighbors to work, like especially as the dimension gets bigger and bigger, and yet it's actually pretty expensive to do this. And so this is one of the main reasons people might not use k nearest neighbors, is that it's just crazy expensive at test time. So it's basically free training, but at test time, every point incurs this this time complexity, which is pretty crazy. And so a lot of the work that's gone into k nearest neighbors is actually to try to fix that in some way, and they're mostly approximate, the ways they do that. And so there's 3 strategies, and I'll just go through them very quickly to give you a sense of what they are. And so one is that you do some pre-processing, so you don't just save the data points, instead you save them into a specialized data structure for which that lookup at test time will be faster, and in particular faster than that terrible time complexity we just saw. Another thing you can do is use a twist on hashing functions, where you try to develop a hashing function that makes things collide when they're near each other in space. And then you try to hash things and get to their nearest neighbors very quickly. And the third one is to try to remove data that's redundant, that's either not affecting the boundary or not having much effect on the boundary. So I'll just say a few words about each of these. So one of the data structures that's quite common with k-nearest neighbors is a KD tree, which is like a binary tree data structure that essentially keeps partitioning the space by repeatedly choosing a point in the data set to split in half. And then it typically will iterate between the axes to do that. So in this example, this is like a 2-dimensional example, so it's going to iterate by putting a split horizontally, then vertically, then vertically. And every time it does, it partitions the space. So for example, it starts by splitting at the line x equals 7. So that's this red line here, x equals 7. And now you go down and you have 2 leaves in the tree, and then in each of those leaves corresponds to the right-hand side of that partition and the left-hand side of that partition, and then you just recursively do this. And so you can see, so then the next one here is 5, 4 would be, so that should be in this direction, and it should be at 5. Then we split by y equals 4. Right, sorry, yeah, this one here. I'm trying to think, what is that 5 doing there? In any case, so you keep partitioning in this manner, and you can do it in different ways. So because I didn't describe right now, how do you pick the point you're going to partition? So that's sort of a heuristic, and one way to do that is to pick the next point as the median of the points being divided. So for example, once I've split this, after the first split, I can look at all the points in here, and this actually is like the median point, and so that is where the next split went. And then you can recursively do this until there are no points left. And so now the idea is that you have a tree, a data structure, that's going to enable you to search for your nearest neighbors. And so how can you do that? So to find the nearest neighbor, you would walk down the tree, picking the path with the closer node, and then each time you're discarding like another half space in that partition that you just created. And so in expectation, this lookup is order k log n now, so it's much, much faster. No dependence on d, and it's only logarithmic in n. But depending how things, there's no guarantee here, so there is like a worst case, and the worst case is that it's still linear and you still have to look through all the data points. So that just depends on how well your heuristic looks for the data you have. And also it doesn't tend to work well in high dimensions, so that's not great. So maybe perhaps a more common thing to do is something called locality-sensitive hashing, so that's the second thing I mentioned. And so locality-sensitive hashing is a technique for grouping points in space into buckets based on some distance measure operating on the points, which makes sense because that's what we need for k nearest neighbor. And so points that are close to each other under the chosen metric are mapped with high probability to the same bucket. And as you can imagine, that's again going to help us quickly find the k nearest neighbors for test time to reduce the time complexity. And so the crucial idea, like if you're used to thinking of hash functions, you're trying to reduce collisions, right? You want like unique hits, and with this, you actually want to group things together if they're close according to this metric. And so another way you can think of this is you're kind of taking high dimensional inputs and reducing them to a low dimensional version while preserving the distances. And that low dimensional thing is going to be the hash. So I'll just give you a sense of how that can work. So it's going to be based on random projections. And so what you're going to do is you're going to take a bunch of data and you're just going to generate a projection at random, like an R vector. And so here's just some random orientation. This is in 2D, but of course you do this in high D. And then what you do is and you're going to do this several times. And each time you're going to basically, now that projection is real value, right? Any point that gets projected, say, onto this purple line has a real value of basically where it falls on this line. And the idea is that you're going to quantize that into a few bins, and then you're going to, for each of those bins, you'll just assign, you'll do it in a binary code way. And then you're going to concatenate all those binary quantized projections into one single hash. So after you've done this, each of these gives you sort of like a quantized binary thing, and then you concatenate them, and now for each point, from all its projections concatenated together, you get like a hash function. Right, and so this is sort of like projecting the data into a low-dimensional binary Hamming space. And each point is mapped to this B bit vector called the hash key. And again, right, unlike normal hashing, we want the hashes to cluster based on their proximity in space. And the reason that that's going to happen intuitively here is because we're doing it like with geometry, right? We're doing projections in the actual space. And I won't go into the details, but again, if you're interested, you can read here, but there's this idea that you want there to be some theoretical guarantees that the probability that the hash function is the same is related to the similarity between them. And you can achieve this in different ways. And so if you have that, now you use these hash codes to find the nearest neighbors. And so one way to think of that is just to have these data points, then you create those hash functions, and now you have a hash table where you look stuff up. And so now at test time, now the training phase includes creating this hash table, right? So when you do these things to speed things up, this now is essentially at train time in order to make the test time faster. And then what you do is you take your test point and you hash it, and that takes you to a bucket where you've purposely put things that are close to it. And then once you're there, then you can look through a small set of data points for your k nearest neighbors. And so this should also be much faster. And this should also actually work better in high dimensions than the previous one. So random projections tend, there are theories about this, tend to work well in high dimensions. Okay, so the last one is to remove redundant data. And so the idea is that you may not need all of the points and your decisions may not change. And so I've actually only seen this for one nearest neighbor. I'm not sure if there's a version that works for more than one nearest neighbor. But in a sense, what you're doing is you're picking prototypes of the data to keep. for test time and discarding the rest because they won't make a difference. And so one way to do that is, and so this is sometimes called condensed nearest neighbor, is you take your training set X and you iterate. So you scan all the elements of X looking for an element whose nearest prototype from you has a different label than X. And then you remove it from X and you add it to U. So you're sort of building up this set of prototypes. And every time you find something that's near a prototype that has a different label, you add it because you know it's going to make a difference. And if it doesn't have a different label, then it's redundant and you just remove it and you don't add it to U. And then you just repeat this until there are no more prototypes added. And so that, like, pictorially, what you're basically doing is you're saying in a region like this, that you can remove this point because these other ones around it have kind of covered that region, right? Like if I'm doing one nearest neighbor for this point or any point, whether this point is here or not is not going to make a difference. And so you remove it, and then you've now lost one data point, and in general, you may have a certain level of redundancy, and you get rid of some number of points, and now the test time, time complexity is correspondingly reduced. And so you can also just look, this is actually from Wikipedia, like this is, I showed this to you last lecture, some data set, and this is the decision boundary for one nearest neighbor, and then you can do a condensed version of the data set, which looks like, actually I'm a bit confused, because that does not look like a condensed version of that. I don't know what's down here. Looks like that's some weird glitch. Huh. Okay, but otherwise it looks condensed. And then, well, so I didn't check this, but then they say that these are what the new decision boundaries look like. So I guess they've done it in a way where the decision boundaries do change. Huh, okay, I just realized now that that's kind of weird. I'll go check that after lecture, what's going on there. So, right, so just a summary of K nearest neighbors from the last class. In this class, we're finishing off this notion of a non-parametric instance-based learning, which memorizes the data. K and N are the simplest example, but they have and they're so simple, but they have these nice theoretical guarantees, and they actually do get used, and they can work well in practice. And people use these various tricks that I just showed you to try to mitigate the cost of test time, where you have to search through every single point if you do it naively. And also, sort of kernels can provide a principled way of deriving non-parametric models from parametric models, and I think I have an example of that very briefly in just a couple of slides. But you can think like what's going on is there's a distance notion here, and so kernels are this thing that measure distance, and if we can put them into more rigorous or principled models, then it gives us a different angle of attack. And I guess sort of SVM was one way to think about that, although it was different, of course. And so anyway, this is kind of a fun slide in the current hyped up world of neural networks. So one of my colleagues pointed me to this, and so it's a paper from, actually I don't know when it's from in fact, but I think it's not that long. And so he said you have to look at make sure the same amount of training data is used, which is 6.2 million things. And so he said Google's fancy CNN is often worse than nearest neighbor, which here is this M2 GPS. So this is a nearest neighbor. I don't know what new means. I guess they've done something into it. And then this is a competitive, like, fancy, deep convolutional neural network. And for several, for half of the tasks, actually, the nearest neighbor does better than the big, fancy convolutional neural network. And so that's also kind of a lesson to check your baselines, like, and just don't use crazy, big, complicated models if simpler things will work. Right, and so, right, this is what I was saying, is the kernels can provide a principled way of deriving non-parametric models from parametric ones. So K nearest neighbors was right. K nearest neighbors is inherently a non-parametric model, and when you kernelize something, you're kind of turning it from non-parametric, from parametric, right? Like linear regression is parametric. It doesn't depend on the number of data points, but if you write it in its kernelized form, then it does. And so, and you get the benefits of lifting into kernel space and things like this, but you now have also turned it into a non-parametric model that depends on having all of the data. So, and that's one sort of an alternative way to think about kernelizing particular algorithms. And so, I don't want to go into this because it's sort of advanced, But this is a particular very, very well-used class of models. In fact, I have friends who consult for Ferrari, and they use this like actually on the racetrack, which are Gaussian process regression or classification. And this is somehow, in a sense, like the most natural probabilistic version of k-nearest neighbors, where you use a kernel to find the distance to all training points, and you have a Gaussian likelihood. And you have to consider all of the data points at test time, just as you do with k-nearest neighbors, and just as there are sort of tricks you can do to speed things up with k-nearest neighbors. Some of the largest open research problems here is how to make it faster and how to effectively get sort of like prototypes and things like this. Anyway, you're not responsible for this, but just for those who are sort of interested in peeking beyond this course, this is a very interesting modeling area. Yeah, and you can read more here and here, but you don't have to. So that's it for k-nearest neighbors. Any questions? Okay, so now we're going to move to decision trees, and these can be used. Most of the slides in the lecture are about using them for classification, but you can also use them for regression, and I'll mention that very quickly. But there's this, I was looking up just to see how different people teach this, and basically 90% of people teach this use this data set, thanks to Ross Quinlan, as a running example. And so since there's some nice slides there, I grabbed some of them and I'll do the same. So this is, of course, a tiny data set with 40 data points, but it's just to kind of walk you through how decision trees work. And the goal is that this is the target variable here, y, and these are the features. So the target's called the MPG. So in the slides, whenever I talk about MPG, it's just a binary variable. We're trying to predict good or bad. And as we do in classification, we're trying to find a function basically that goes from x to y. And right now, these are discrete data in most of the examples, but at some point I'm going to start mixing in features that are real value. And so one of the strong points about decision trees is if you can very naturally mix discrete features or categorical features and real value features, which can be more difficult in other settings. So what are decision trees? Again, this is one of these classes where it almost tells you in the name what it is. It's a tree where at every internal node, you're going to test one of the features. So here, attribute is the same as feature. And you're going to say, like, in the case of categorical, you'll just have a branch for every possible value. When it's real valued, as we'll see, you're just going to split on a threshold. You say, is it above this or below this? And you basically do this recursively. So you take one of the features, and we're going to get to how do you pick which feature to split on and in what order. But like generally, just at an abstract level, you will be splitting on a feature, then you split on another feature, and so on. And by the time you get to what we call as like a leaf node, is you then at classification time, you just take the majority vote of all the training examples that ended up in that leaf. Or again, you could create like a probability from it as you would with your k-nearest neighbors. This is a general idea clear. It's just like a really sort of simple tree, but these are really, really powerful. Like we use these all the time, and they're somehow very simple, and they're also kind of human interpretable, right? Like you can actually read off rules. And in fact, in some sense, these are like the decision trees are like the game of 20 questions of machine learning, right? You know, like you're trying to pin something down. You say, well, is it, you know, black or white? Is it alive or is it dead? And so like kind of this is what the decision tree is doing in order to make a classification. And so what it's actually like in a more from a more formal perspective, it's chopping up the space, because every decision is chopping up the space in an axis-aligned way. So if you have just two features, and in this case these are real valued features because you can see I'm splitting it in multiple places, then basically what the decision tree can do is it can arbitrarily split the whole space arbitrarily as long as it's axis aligned, because I'm making splits on features, and every split therefore is making an axis aligned partition of the feature space. And then once you've finished splits, then whatever lies within a given coherent region has some number of positives and negatives from the training example, and then you can take a vote. It should not say extensions next week. That is from Nissan. So, right, and so a consequence of that though is that, right, as I keep saying, these are axis aligned, and so they can't easily model diagonal boundaries. So imagine you had data that looked like this, in like a toy example of 2 dimensions, which we've seen, and we know with all the other classification models, we can slap down any linear boundary, right? Like even with the simplest model, like linear discriminant analysis lets us do that, non-kernelized SVM lets us do this, logistic regression lets us do this, but the decision tree actually doesn't, right? It's gonna have to like make a whole bunch of weird axis-aligned partitions that all together allow you to do this. And so somehow it's wasting some of its decision boundary when it could do something more succinct. But that's okay because they're still very powerful models, and so they still do well. But right, it says waste most of the model capacity on useless boundaries. Of course, this is maybe an extreme example, maybe not. But they can be really accurate. So like some of my most recent application papers have actually used these. And somehow the fact that they're nonlinear and so simple makes them really powerful despite this weird artifact. Okay, so and then like we're gonna have a whole bunch of toy examples here, but these can of course be like quite big. So this is just like to give you a sense that they're not always these toy little examples with 3 or 4 nodes. Okay, so what hypothesis space is this class of models? So I said it's these trees, and what we can do is that at each node we can take some of the features, which are these guys here, and then make some split on them, either real values into according to a threshold, or just break up all like categories. So it turns out that they can, in the say Boolean case, the decision tree can represent any function of the attributes at all, because basically every path from the top to the bottom is essentially a row in like a truth table. So like if you're not convinced of this, like when you go home and you look at these slides, just think about this, that you can arbitrarily create any Boolean function here. But the issue, as it's written here, is that this may require exponentially many nodes, right? And in general, in machine learning, we don't want to just fit any function arbitrarily because the odds that it generalizes are pretty poor, right? So what we know is these have sort of very high capacity. They can kind of represent anything. And then the trick is always going to be like, how do we use them in a way that they generalize well? So we'll make our way there. And so you might ask, like, imagine you have a training data and you are trying to get down to 0 training data. Is it possible that actually more than one tree gives you 0 training data? And if so, how are we gonna choose the best one? And things like this. And so okay, so let's first look at how we split the nodes, which I just keep saying we're going to split. And so let's now look at detail at how people actually do that, and then we'll consider finding the best tree. So what is the simplest tree? So again, I have this one target variable here that's good, bad, and in this case I have 1, 2, 3, 4, 5, 6, I guess 7 different features, and here they're all discrete. So the simplest tree would be just the root node that basically is not making any decisions. It just predicts the majority class. It says the majority, if I go look here, there was more bad than good. So the root node by itself is just always going to predict bad, and in this data that means it gets 22 things correct and 18 wrong, so like that's not great. And then the idea is that each time, like, it's going to get slightly better every time we add a new node, and that we're going to do this recursively. And so I noticed actually, I didn't want to lecture on statistical tests, but I noticed this was in all the slides, so I just went back, and this is a side note. If you're wondering what p-chance is, it has to do with a statistical test also that can be used. It's a simple chi-square statistical test, but let's ignore it for now. I just wanted to point it out in case people were wondering what it was. So basically just ignore it, and if you want, you can find out more about it. So I said the simplest tree would be just the decision stump. Just the root, and then sort of the next simplest one is called the decision stump, in which you're allowed to pick one feature to split on. And actually, in a couple of lectures, when we talk about boosting, we're going to talk about decision stumps, which is like a very constrained model because you're only allowed to pick one feature to make decisions on it. And so now it should be better than just the root node, but probably not that much better. And the idea is that we're going to increase the complexity by recursively partitioning. And so if this was like the original data, then we're going to essentially, every time we have a node, we're going to push part of the training data down one of the paths according to the nodes, and then we're going to recursively split that and recursively split that. So, right, so imagine that we picked cylinders as the first feature to split on, and cylinders has the value 3, 4, 5, 6, and 7, and this is how many data points of each class lie in each of those buckets. So if this was the only thing we use, then the predictions for this bucket would be bad. I guess there's a tie here, so when there's a tie, you can just arbitrarily flip a coin. In this case, there's more of good, so the prediction would always be good, and so on and so forth. And so now the idea is for each of these, we're gonna now recursively build a tree with the training data that ended up in this bucket. So not with all the data, but only the data that ended up in this bucket. And so in that way, we're gonna recursively partition the space more and more. And so now we can add a second level where right now it's showing just for, it's expanded out this node into these three things based on the maker being America, Asia, or Europe. And it's also expanded this one out into horsepower here, 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 and so on and so forth. So you can keep going and you can get like a full tree. And unless you have weird things in the data, so like if you have no noise in your labels, then you can always get zero training error. You just keep going until you get zero training error. But the question is, like, is there some trees that are better than other trees? And so, right, any tree, we know that any Boolean function can be represented by any tree. And here's an example for this Boolean function of two different trees that represent the same function. You can double check that at home after. And so does someone have a sense of which of these we might prefer? Who prefers the one on the left? Who prefers the one on the right? This is very uneven vote. Huh, interesting. Who voted for the left? Who wants to explain their reasoning? Yeah. You want a shorter tree. Why do you want a shorter tree?
Less variance, more generalizable.
Yeah, roughly. So yeah, I mean, it's a little bit heuristic. So there's something you'll often hear in machine learning called Occam's razor. It's just a principle basically of simplicity that basically says don't use more complexity than you need to. And so that's a little bit in the eye of the beholder, but I think we would all agree that this one is simpler than this one because it's somehow like a smaller tree. It's got only a depth of 2, and like you could count the edges, and there's fewer, right? So it's sort of, I think, unambiguously smaller, and therefore probably unambiguously less complex. And so this is a heuristic, but a sort of very, very common heuristic. And so two competing theories that make the same predictions take the simpler one. But you can also formalize this a little bit, which is that there are, like, if you start counting like the statistics or use a mention of the variances, like how many short models are there versus long or large models? And so of course, the larger the model, the more such models there are. And so the more likely it is you just sort of randomly fit the data by going on and on and on. And so the idea is that you're less likely to have overfit your data with short models. And so generally you should prefer short models. Okay, so it turns out that if you have your training data and you want to actually compute the smallest decision tree that gets all the training data correct, this is actually intractable, right? So this is like NP hard because you would have to basically search through every possible tree, and so this doesn't scale. And so actually no one ever does such a thing. And instead what you do is you resort to a greedy heuristic, which is you start from an empty decision tree, and then just as I was showing you, is you slowly build it up by picking one attribute to split on, and then another one, and then another one. And when the attributes are categorical, you're only allowed to use that attribute once, and then it's done. So you're only allowed to make decisions with it once. When you have a real valued attribute, then you might split on some threshold of it, and later on you might split on a different threshold of it, so that you don't have the same rule there. So, and now the question is, okay, so we now know we're gonna start, we're gonna do a greedy procedure building up the tree because we can't do the full search through all trees. And now the question is, how are we gonna pick those attributes to do the greedy search that goes forward? And so the idea is that basically every time we're at a particular part in this iterative recursive scheme, we're going to say, well, what if I pick this attribute next? What if I pick this attribute next? What if you're going to try for every attribute, and you're going to compute some sort of a score that says, like, how much better will the tree be if I split on that attribute, or that attribute, or that attribute? And the way you're going to do that is to use the counts, like at the leaves of each possible attribute. That tells us something about like the uncertainty of the class, because the idea is that by the time we get to a leaf node, we want to have no uncertainty about the class, right? We want everything that got to that leaf node to have all the same class, or roughly so. And so, right, a good split is if we are more certain about the classification after we've done the split. And so, as an example, maybe after you make a split on a particular feature, maybe it becomes deterministic. Maybe everything in that bin is all true or all false. If after in contrast to that, if you make a split and all the data there have uniformly the same probability of all the classes, like this is not a useful split, right? You haven't. The idea is you're somehow trying to make each split. You want the data to be more pure for one of the classes, such that you're making headway. But of course you can't get there right away, and so you could just say, does this split make it perfect, yes or no? But how do I do something that's like in between, given that it's not going to be perfect for a while? And also at some point we're going to talk about the overfitting, and so you may not want to go until it's perfect anyway. So we're going to go back to some of these ideas from information theory that we've seen at least once, maybe twice. And so we're going to think about entropy now, and how entropy can let us think about how to pick an attribute or a feature to split on. And so one nice way to think about entropy is as a measure of expected surprise. So the surprise of observing that a discrete random variable y takes on value k is essentially log of 1 over its probability, and then I can just pop that up and put a minus there, right? So, I mean, think about this. If the probability that y equals k is actually equal to 1, then I have 1 over 1, and log of 1 is 0, so I have no surprise at all, right? And if the probability of that is really, really small, then I have a huge number here, and I take the log of a huge number, I still have a huge number, so that like my surprise is really, really big. And so this is somehow you can think of the entropy well, this isn't, sorry, the entropy yet. This is just the surprise factor. And then, right, so as p goes to 0, the surprise approaches infinity. This is what I just said. And as it goes to 1, the surprise approaches 0. So that sort of makes sense intuitively. And so what the entropy is the expected surprise. So you take the distribution over all possible values of y, and you compute the surprise. So that's another way to think about entropy. Also, as we described it before earlier in class, like high entropy means like a very flat distribution, and low entropy means like it has peaks and troughs in it. So just as an example, if you imagine flipping a coin, and so there's a probability, is the coin fair or not? So a fair coin is 0.5, which is in the middle here, and then as you change the value of the probability of heads to closer to 0 or closer to 1, you can see how the entropy of that distribution changes. And so, of course, the entropy, or the expected surprise, is going to be highest when the coin is 0.5, because that's when we have least certainty about what's going on, right? If you have a very biased coin, then you're not going to be surprised at all, because it should just keep flipping heads, for example. Okay, so right, and I mentioned this just now, but just to emphasize, high entropy is from something that's like a uniform distribution, or it's like a flat histogram. The values sampled from it are less predictable because they come from the whole space. And low entropy is where it's the opposite of that. So somehow, like, parts of the space you don't expect to see it from, and so in general you tend to be less surprised. So, okay, so why are we talking about entropy? We've been talking about how are we going to pick a feature to split on. And so it's going to be related to these information theoretic concepts like entropy. And so, okay, let's think, is it going to be the entropy of the target variable? Can that somehow help us? And so, well, no, I have no control over that, right? These are just my training data. The entropy of this, it is exactly what it is, which is, I think, is that on the last slide? Yeah, this is actually the entropy of the target variable in this toy data set, and I have no control over it. It's just given to me. So, can anyone take a guess what we do have control over that's related to entropy? How can you think of some way we might use entropy to pick a feature to split on? Yeah, right. We're going to condition on features and ask how the entropy changes. with the idea that like by the end of getting to a leaf node, we want the entropy to be as low as possible, right? We want no surprise. We want to know with high certainty what class it belongs to. So we kind of want to drive the entropy down, and so we're going to do something that kind of that does that. And so and we're going to do that by conditioning on X and ask, like, if I were to split on this value, then conditioned on X, how does my entropy change? And then we're going to recursively do that. So the idea is to drive the entropy within a leaf node to be really low, and correspondingly on the way there, we want to keep reducing the entropy of the different buckets. And so to do that, we're going to use this notion called conditional entropy, which is like the entropy of Y conditioned on X. So let's just go through what that is. And so it's basically the way to think about it, and is that you're going to, after you've done a split, so what this terminology is, right, is that, and now this is real valued features, is that the split is that either feature J is less than V, or feature J is greater than or equal to V. So that's the threshold that we're going to pick, and we'll get in a second to how you pick that threshold. But so the conditional entropy based on that is the probability that you belong in that split times the entropy of Y given that you're in that split. And then we're just doing a weighted average here. So this is the weighted average of the entropy from each of those two sides, and the weight is just proportional to how much is in each of those two splits, right? And so that's basically what it is. It's like a weighted average entropy conditioned on that you've split into two partitions. This is the entropy of the one, the entropy of the other, and then you're just weighting them by the probability that you ended up on the left side or the right side. And so you can work through another example here. If you just want to see the numbers, I'm not going to go through it. So the idea is going to be to look for splits that reduce the conditional entropy so that I get to these very pure nodes. And pure, you'll hear this word purity in decision trees. The idea is like, right, you want pure means like the class labels are all the same the further down the tree I go, such that at the bottom, like I know what class it is and I'm not surprised. So just some properties in general about entropy and conditional entropy and joint entropy. You can actually use the chain rule as shown here, as you do for probability, which follows from the laws of probability. And also just intuitively, if X and Y are independent, then X doesn't tell us anything about Y, so the entropy of Y is the same as the conditional entropy on X. But of course, Y tells us everything about Y. So if you tell me Y, then there's no more surprise left, so it's 0. And the other thing is that by knowing something, you can only decrease the uncertainty about Y. And so therefore, the conditional entropy is always less than or equal than the unconditional entropy. Okay, so back to, this is just the slide from before, this idea of conditional entropy. And so, right, the goal is that at each recursion is to find the feature and the split. If it's a real valued thing, then we need to also find, right, which threshold, which minimizes the conditional entropy. Any questions about the intuition of this? Okay, and so equivalently, actually the word you'll normally hear in decision trees is not to maximize the, to minimize the entropy, it will be to maximize the information gain, and that's because the information gain is just defined as the entropy minus the conditional entropy. So since we cannot change the entropy of Y, that's always fixed, this is the only thing we can change, and so if we maximize this, then we're minimizing the conditional entropy. So it's the same thing. And normally you'll hear about the information gain as the thing that you're trying to maximize. And then, right, and that's because this is basically the information you had in some sense, and now it's the information after making the split, and the difference between these is how much information you gained by making a split. And the information here is like information about the class, right? Like again, like think of this as trying to get to make a prediction. And there's also an alternative that I'll just mention because it's also commonly used called the Gini impurity. And this is somehow actually quite similar in some ways to the conditional entropy, and it measures, well, the entropy and the conditional entropy. So it measures how often a randomly chosen element from the set would be incorrectly labeled if it were randomly labeled according to the distribution of labels in the subset. That's like kind of a mouthful. Right, so you have a set of data, and imagine it's in two classes, And so if I choose, first of all, when I choose a random one, then it's in proportion to the proportion of those two classes. And then I'm going to label it in proportion to also that same thing. And basically, this is the Gini impurity. So it's computed by summing the probability of an item with label K being chosen. And so that's just according to the proportion that it's there, times the probability that you would make a mistake in categorizing it. So the probability you would make a mistake in categorizing it is the sum over all the other categories, right? So if there's K categories, you sum over all the other ones, and that's the probability that you would misclassify it. And so you can just write that as 1 minus P sub K. And so, right, so the G, and if you push this around now, over all, if I write this out, those two things, and sum over all K, I end up with a Gini impurity measure, which is just 1 minus PK squared. And it's getting at the same idea, which is that if I imagine I have only a single class in my bucket at the time, then that means that one of the Ks has all of the stuff in it, and the others don't. And so the Gini impurity is just going to be I think there's a sum missing here. There should be a sum here, but so what it will be in that case is a 0. There is no impurity at all. It's completely pure. But I think there's a sum missing here. I'll fix this after. And then you get this conditional Gini impurity in a similar way that you get the conditional entropy that you can pick for binary node splitting. And again, similar to entropy, you're going to weight it by the partition as you do with the information gain. So now you take the Gini impurity of all those samples that were in the one split times the probability that they were in the split, and again, that they were on the other side of the split times the Gini impurity of the other split. And so empirically, this tends to yield similar trees to information gain, and you'll probably hear about both of those. Okay, so right, so again, how do we, now we have these measures we can use that are basically meant to make each, get to buckets that are pure, that have only one class. And so we're gonna sort of in this greedy manner, we're gonna start from an empty decision tree, and then we're gonna split on the next best attribute according to one of our chosen measures. And so different algorithms have different names, I can't remember, but like there's I think something called like C4.5 or ID3, and like different versions of decision trees you'll see in like scikit-learn and stuff, they basically have different heuristics, like they use information gain, or they use Gini impurity, or this or that. So like a whole bunch of different flavors of decision trees out there. But the idea is you pick the next best attribute, you make your split, and then you keep going. And so in that example, the running example we have, in this case, you can at the very first split, like when you have just the root node, what you do is for each of the categorical variables, you can if you compute the information gain, if you were to add it to the tree, and then you pick the highest one. What is the highest one? Information gain, it's this one. All right, so hopefully they did add cylinders first. Right. And so for categorical features, you could also, you don't have to split into all the categories. You could, in principle, split to one versus the rest. So, I mean, some of these things are just user decisions. Some of them are standard practice. So for categorical, usually you do break it out into all of them. And so I mentioned that you could pick a real value one. And so how would you pick a threshold for a real value thing? Because in principle, there's infinitely many thresholds, right? So but of course, as we saw with actually ROC plots, the number of these, like in principle, there's an infinite number of thresholds, but we have a finite number of training data, and so there's only so many thresholds that will actually make a difference according to the training data. So we only need to try that number of thresholds, and right, oh, sorry. And this is, just how you write so entropy is usually written for discrete stuff, and so, and the categorical variables, this is just saying how you can generalize it when you're splitting. So now you do, and I think this was earlier in the slides, so instead of just being, is the variable equal to a discrete value or not, now it's just that is it less than or equal to the t, or greater than or equal to the t. And then also note that you can try every possible threshold between all the data points, but you don't even need to try all of those, because if you, because some of them will be redundant, right? Only splits between examples of different classes actually matter. Because it's just one scalar feature here, because you're picking one attribute, and then you're going to try all the possible different thresholds that might make a difference on the actual training data. And so in that case, instead of saying like, was it Asia, was it Europe, you get these branches that will look like, is it less than 78 or is it greater than or equal to 78? Okay, so what we've talked about now is that finding the best tree is MP complete, and instead we use a greedy heuristic. And then I talked about how we can use this concept of information gain, where we can now greedily pick things according to the information gain, always trying to gain more and more information about the class. And so the question is, like, when do we stop? So we said that basically we can get zero training data, but that's also true, like, if you go back to like the first couple of lectures in this class, when you were doing linear regression, if you added enough polynomial features, you could always get down to zero regression error, but that's never what you do, right? Because we know that that's overfitting. And so somehow, if you do what I just said here, you're basically always gonna overfit. But even before we talk about overfitting, I still haven't described how we just stop. Imagine you're willing to have zero training data, then in fact, I still haven't told you a stopping procedure. And so what are the kind of times where in this procedure you say, I'm not splitting this node anymore, like not because of overfitting, but just because like I can't do anything, I cannot make progress. So what's an obvious one is that if I get somewhere like here, cylinders, and in that example, remember when I went to the third layer, I said it expanded this one and it expanded this one. The reason it didn't keep going with the other three is that they had a limit, like you could not do anything more. Why not? Here is that all the matching records have the same output value. So these are basically already completely pure. Once something ends up here, then it has like probability 1 of being in that class that's dominating. So there's nothing more you can do in that case. So that's sort of one way you would stop recursing on a node. A second case is if imagine that you don't have that, you don't have this purity, but what you have is you have all the remaining features are identical. Then there's nothing you can do, you're just stuck. So that's sort of the second case where you these are just trivial cases where you just throw up your hands, you say like, it's clear, like I don't keep progressing on this node. In the first case, it's good because you have this pure node. In this case, you just you don't have any more features that will let you partition the space anymore because all the feature values are the same. Okay. So that was these two, and no one would dispute these. And then, and some algorithms will do the following, and some of them won't. So here's another case where you might want to stop recursing on a node, which is if all the attributes have zero information gain. So who can see why this might be a good idea or why this might be a bad idea? Okay, I'll give you a hint. Imagine you had an XOR function, so the standard XOR function, and you computed the information gain on feature A and on feature B. So feature A, feature B, 0 and 0. So if I use that base case 3 for stopping, it's going to not split on any node. It's just going to use the root node. And the root node is basically 2 and 2, so you can toss a coin and just say, okay, I'm going to make it always predict 0. So it's actually not going to get zero training error. And in contrast, if I remove that base case 3, if I say, you know what, I don't care if I don't get any more information gain, I'm going to keep going on. So I said, what's gone wrong? It's not clear that something's gone wrong, but it's something to ponder. So basically, I'm using a greedy heuristic. And what's happened is because it's greedy, I've stopped it, even though if I keep going, I could get to zero training error, which we may or may not want to do. So if I allow that if I don't allow that base case for stopping, then I will keep growing it, even though there was no more information gain, and I will have zero training error. And so all that says is you may or may not want to do that. And again, as with all the machine learning basically that we're telling you, there's always a rigorous part, and then there's always an art of okay, what do I do? And this typically comes down to empirics and knowing how to run experiments to convince yourself in a rigorous manner that something works well or not. But often what people do is they don't care if the information gain is 0 or not. They will still keep going, and then after the fact, they will then go backwards and prune the tree of things that are not helping a lot. And you can do this with a statistical test that I kind of alluded to, or with holdout performance that I think I'll mention more about in a second. So basically, you can now we have all the ingredients, right? We start with a non-tree, or just the root node, and then we greedily add values. And then basically what this algorithm here is mostly doing is just encoding those stopping criteria. So given some data set and some output, and this is going to be called recursively on each node. So output here, I believe, are just the targets. It's like a weird language, predict this unique output. Yeah, I think these are X's and these are Y's. Sorry, I should have changed it. So right, it says and now this is base case 1, says if all the output, all the target values are the same in this data set, then I'm not going to split it anymore. I'm going to stop, and I'm going to return a leaf node that just says predict whatever that class was, that unique class that falls into that bucket. On the other hand, if all the input values are the same, then I'm going to return a leaf node that says predict the majority output. So if all the X's now all look the same, then I cannot split anymore. There's nothing else to be done. So the best I can do is just predict the majority. So in this case, I have a pure leaf node. In this case, I have a non-pure leaf node on which I cannot make progress. And if I'm not creating a leaf node, then I'm in the position to find the attribute with, say, the highest information gain or Gini impurity. And now, for each of its distinct values, if it's a categorical class, then I'm going to create a non-leaf node with each of those things as its children, and I'm going to call this recursively. And so that's basically the whole thing, right? Is just to decide when to stop. When you stop, you create a leaf node, and then depending which case you're in, you either predict the unique class that's there or the overall the more prevalent one. Okay. So this has a fundamental flaw, right? And so it's going to keep going until the data are perfect, unless you have some noise. Like imagine someone gives you 2 identical X's that have discordant Y's. Then you can't get perfect training data because you have data that's inconsistent with itself. But if not for that, you will always get perfect training data because you just keep going and keep going and keep going. And so this is, like, as I said, this is sort of akin to saying, I'm going to keep adding polynomial basis functions until my regression error is 0, which we know to be stupid because of the bias variance trade-off, right? So we would never do that, and so nor are we going to do it here. And so the question is, how can we fix this with decision trees? And so, so these naive decisions, I also grabbed this from somewhere. It's really interesting because they said standard decision trees. But these are not standard. No one would do what I just said, right? So it's not standard as a naive decision tree. And so the training set error is always 0, and it's going to have lots of variance because of this bias variance trade-off. And so what you need to do is you need to somehow introduce a bias towards simpler trees. And so there's some common ways people do that. So if you go look at scikit-learn, which you're not allowed to use on the Accordion assignment, but in real life you could, then you'll see parameters for like the maximum depth. So maybe you say, I don't want any depth more than 5, maybe not more than 10. And these are going to be things, hyperparameters that you should cross-validate over using this nested cross-validation. You might fix the number of leaves, and there's a variety of things. So, and so I see, I mixed and matched. You also might limit the number of points, the minimum number of points in a node. So you might say, if I get to a node that has fewer than 10 data points, I refuse to split it anymore because it seems like nonsense. And then I mentioned this also, you might fully build the tree, and this is pretty common, is to build it maybe even up to a max depth, and then you go back and you prune it. And you could do it in different ways. You can prune it using statistical tests where you say, did I really need this? Like, what's the p-value that I needed this split in the tree? If I didn't really need it, I will remove it. Or you can just actually use like a validation set or nested cross-validation and say, what if I remove this node and all of its descendants? Does my generalization error according to the validation set go up, or does it go down? And you can just keep doing, now you kind of greedily go backwards. You grow it greedily forwards, then you grow it greedily backwards. And you can also have sort of different early stopping criteria, like the depth of the tree and things like this. But or the information gain, you could use that one that the information gain is 0, but then you may be subject to this problem of base case 3, which is in the eye of the beholder whether that's good or bad. And then the other thing you can, and actually probably the most common way anyone uses a decision tree is to build a bunch of them and combine them together. And this is called like ensemble machine learning. And with decision trees, I don't know if you'll ever see a real application, maybe, where you use just the decision tree. Usually you compute a bunch of decision trees, and we're gonna get to that, about how do you create different ones and how do you combine them. And this is sort of a whole area of machine learning called ensemble learning, where you produce many of the same model in such a way that they're different, and then you combine them together. So there's in the actual class notes, there's this figure about why you shouldn't use misclassification error. And I find it, I don't know, I glanced at it and it didn't seem super clear to me. Did anyone read it? Some of you read ahead. I'm curious if it made sense to anyone. Okay, maybe it did, I don't know. All of our brains work differently, so that's why we all teach differently. To me, this is the nicest explanation of why you don't want to use misclassification. So, right, in the beginning I said we're gonna just use these information theoretic principles to find a value to split on, like information gain or like Gini impurity. And you might say, well, if what I'm trying to reduce is the misclassification error, why don't I just split on things that keep reducing the misclassification error? And so basically, no one actually does that because it doesn't work well, and there's, I guess, different ways to think about it. So for me, the way to think about it is as follows, is to select the best split, we're gonna aim to maximize the decrease in some impurity, like the Gini impurity or the conditional entropy, right? And so let's think of V1 and V2 as two children of the parent node. And we're like, there's basically values, right? And so there's going to be the probability of all the things, these are sets. So V is the parent set, and V1 and V2 are the two children sets after you've done a split. So the probability of V1 is just like the number of things in V1 over the total number, so maybe like 3 over 10, and maybe therefore this is 7 over 10. So let's say 0.3, 0.7 is just how many things go into each of the two splits. And so the decrease in impurity is going to be, wait a second, right, so, and here I'm now using this general thing, this is the entropy, or so this whole thing is the information gain. Actually, it's funny, I thought this was clear, now it's confusing. So this whole thing is the information gain from a split to V1 and V2. And I might clean up these slides a bit also, sorry, they're not as clear. But the main idea is that these different functions like information gain and things like this, there's different things you can plug in here, Gini impurity, and it turns out there's a property of them is that if they're concave, then you have this property that the decrease in purity is greater than or equal to 0. And if they're strictly concave, then this thing is actually strictly greater than 0. So I'll just give you the sort of intuition here, which is that if you have these functions like Gini impurity and information gain, if they, and there's a picture, if they have this concave property, then you get a guarantee that every time you make a split, you're going to do better by that criterion. And so you don't hit a dead end, basically, is what it amounts to. But there's also another intuition, which I don't think I have in the slides, which is if you think along these lines a bit more deeply, what you'll also find is that if you try to evaluate different nodes with the misclassification rate, you'll find that like things that are quite different by Gini impurity and by the entropy actually all look the same, even though it's pretty clear some of them are better. And intuitively, what's going on is misclassification rate has a threshold effect, right? The idea is that I'm now like looking at and classifying things inside this measure by whether they're greater than or less than 0.5 in the binary case. Whereas with entropy, there's no thresholding effect. With Gini impurity, I'm using sort of the full probability distribution. So that's the main intuition, is that they're not very sensitive to the partitioning. Right, so, okay, I think I didn't do a great job explaining this, but actually this is in the discussion, so we'll make sure that, I may try to do this better at the beginning of next class, although we have a guest lecture by Anand Sahai, who's gonna actually tell us about some of his recent work and the bias variance trade-off, and he's a fabulous lecturer, and you are responsible for the material, so you have to come anyway. And that's why a few lectures got moved around. So I may try to clean this, because I think what I just said here was I didn't do a good job explaining this to you. So it will be in discussion, and I might come back to it at some point before we continue on. Okay, so I'm gonna, okay, but let me just say a few more things since we have 5 more minutes. So there's also, in fact, people don't usually use information gain because it's biased toward tests with many outcomes. What that means is if I have a categorical variable, like maybe I'm saying, should I split on engine type or should I split on country? If I have 100 countries and I have 2 engine types, information gain will be biased towards the one that has many different categories. Because I basically am just, it's somehow there's like a currency I get to use up of splitting into many things, and it shouldn't be that way. And so as an example, consider like a feature that uniquely identifies each training instance by the category. So now I just naively split it up by category, which isn't actually helpful, but I get like sort of maximal information gain just because I had so many categories for that variable. So this is actually not really helpful. And so what people do is they fix it using this thing called the gain ratio. And so what they're going to do is normalize the information gain by sort of the information of the split by virtue of how many categories it has. And so, and what it's going to do, it's going to essentially be like a penalization factor for highly branching variables, such that for them to get chosen, they have to have even higher information gain. And it takes into account the number and size of the branches. And so it's going to do this by this notion of like an intrinsic information of the split, which is by virtue of like how does that split look? And so you'll hear this term called like split information, and this is the thing just on the next page, I'm almost done. What we're going to end up doing is we're going to take the information gain and we're going to divide it by the split information, and we're going to use this quantity to pick the next attribute, which is going to debias it against these like highly branching categories. And so what is this? It's really just the entropy of the partition. Here, so that basically, if I have a variable that splits into many categories, and the categories are split very evenly, then it has a lot of entropy, and I'm sort of just going to win by virtue of spreading things out across all those different categories. What I actually want implicitly is like somehow an effectively smaller branching factor. What does effectively smaller mean? It means that even though I have all these categories, that it's not uniformly evenly split up. I have more stuff in some of them, and some of them don't get used very much. So that partition sort of has lower entropy, and those are the ones I want. And so in some sense, what I'm doing is I'm normalizing by the entropy of the partition itself to penalize against variables that have many, many categories. And then just one last thing, I mentioned this in the beginning, you can use these for classification, as we've been talking about. You can also use them for regression. And so we're not going to go into details, but basically you could predict the mean of those in the bucket, or you could augment it with linear regression. And then instead of trying to minimize like the classification error, you're trying to minimize the mean squared error. And instead of using things like information gain, and all these things are only applicable to like discrete classification, instead what you typically do is you minimize the sum of the variances after a split. And because here, the notion of purity is not that you have all the same class, the notion of purity is that all these things have almost the same regression value, right? So you want them to be clustered together and have low variance. Okay, so I'm going to stop here and I'll try to clean up that other thing. Thanks.